This presentation on design synthesis in a virtual reality environment was prepared by Douglas Maxwell, Rob King, and Allie Butler. This research effort was conducted through collaboration between the Naval Research Laboratory and Louisiana Tech University, with financial support provided by the Office of Naval Research. The goal of this research is to demonstrate application of immersive virtual reality methods to accomplish design synthesis of complex mechanical systems, such as ships and aircraft. The fundamental premise of this research is to explore the use of stereoscopic vision for viewing and interacting with an engineering design environment. Stereoscopic vision permits depth perception by presenting different views to the right and left eye. The use of stereoscopic imaging provides perception of three-dimensional existence. Although this videotape cannot capture the immersive 3D experience, it does provide an overview of capabilities. Our hope is that the virtual design environment that permits stereoscopic vision can be used to advantage in design tasks by engineers and naval architects by providing a three-dimensional immersive design environment. To produce a stereoscopic image, shutter glasses are used, which alternately shutter the left and right eye at a rate of 120 cycles per second. The images produced for viewing through shutter glasses alternate so fast between the left and right eye that the shutter activity is not perceived by the wearer. Synchronization is maintained by an infrared emitter that transmits signals to a receiver between the lenses of the glasses. The images on the floor and walls are produced by CRT projectors that reflect light from a mirror to a translucent or white surface. The images are produced on left, front, and right walls by back projection. And on the floor by direct projection. This configuration, located at NRL, is called the Graphical Room for Orientation, Training, and Tactical Observation, or Grotto. The Grotto is an immersive environment developed by the Mechdyne Corporation. Objects in the user's workspace are stored and manipulated in a software structure called a scene graph. The scene graph contains data that define the virtual world, including low-level descriptions of geometry and their appearance, as well as higher-level spatial information, specifying position, animations, and transformations of objects. The scene graph is a data structure that facilitates computation of the scene in the virtual environment. The high-fidelity, fully rendered graphical images are generated on an SGI Onyx2 with 2 graphic pipes and 4 raster managers. The software employed includes the IRIX version 6.5 operating system, SGI Performer version 2.2 graphics library, and OpenGL. The user's position within the grotto is tracked by an Ascension Flock of Birds magnetic tracking system. A receiver attached to the user's eyewear provides the position and orientation data necessary for accurate stereoscopic projection calculations. User interaction employs a flight stick constructed at NRL. Physically, the flight stick interaction device consists of a modified PC joystick, tracking system receiver, and an interface box that reads the joystick buttons. Interfacing to the device is accomplished using client-server software called the Virtual Reality Peripheral Network, or VRPN, provided by the University of North Carolina, Chapel Hill. The virtual design environment includes a design space on the rear screen and floor. Synthesized geometry is displayed on the rear wall and floor of the grotto, with the right and left walls used to support interaction. On the right wall is a tool cabinet for 9 tool tips that are used for interaction with the design space. Each tool tip represents one form of interaction. For example, the rotate tooltip is used to rotate geometry about an axis, and the sphere tooltip is used for generation of spherical primitives. In each case, appropriate tooltips are removed from the cabinet for use with a tool handle. The graphical representation of the tooltip in the virtual environment is changed to provide visual feedback for the user selections. The tool handle is used to implement the action related to the different tooltips. Additionally, a stand called the pulpit is present for the keyboard. In this demonstration, interaction is accomplished with the flight stick, but in other circumstances, interaction could be implemented with data gloves or other devices. The flight stick has a ray that extends from the tool handle into the design environment or to the tool cabinet. This ray on the flight stick is called a laser pointer. The laser pointer facilitates selection of tools or objects in the immersive environment. The left wall of the grotto contains a calculator used to assist the engineer or naval architect in the development of a design. The calculator uses the XCALC utility, commonly available in the X Windows environment. Other interaction is also available on the left wall of the grotto through an open IRIX window, allowing designer communication with the computer system. In the current version, synthesis of geometry is accomplished using geometric primitives. These primitives currently available include boxes, cylinders, cones, spheres, an annulus, referred to as a pipe, and NURBS surfaces. The primitive is selected for use, and the system automatically gives the primitive a unique name, generates the primitive with unit dimensions, and places the primitive at the origin of the axis system. The primitive can then be manipulated by changing dimensions through scaling along each axis, changing orientation through rotation about each axis, and by translation in each dimension. The manipulations are controlled by user gestures using the flight stick. By using the scale, rotate, and translate functions, geometry can be sized and placed in desired configurations by simple gestures. As an illustration of this capability, a cylinder is generated. At inception, it has unit dimensions and exists at the origin. However, it can be reshaped by scaling along an axis. Note that the letter S is displayed to signal scaling operations. Also, the cylinder can be repositioned by translation and by rotation. The letters T and R are displayed to signal those operations. Further synthesis of geometry can be illustrated with an example problem in mechanical design. In this example, components for a universal joint are synthesized beginning with a cylinder. In addition to the cylinder, a box is generated, and the box is scaled and translated to become part of the universal joint. Next, the cylinder is translated into position. These actions occur through gestures with the flight stick. After repositioning, a geometric primitive may need to be moved or its shape altered with gestures. This is done by selection using the laser pointer. Upon selection, the primitive is then moved or altered with gestures as needed using the scale, translate, and rotate capabilities. Once significant three-dimensional geometry is synthesized, it should be saved in a file. For this action, the keyboard is used. As a part of a mechanical design, the current geometry is saved to a file called partial. As an action that restores geometry from a saved file, the load function is also available at the keyboard to restore three-dimensional geometry from a file. As an illustration of this capability, a more complete universal joint model is restored from a file. As a three-dimensional immersive model, examination and review of this geometry from any angle or perspective is possible. The user can even view an object from inside that object. Because the viewpoint from your TV screen as you watch this video is only two-dimensional, you cannot experience this effect. But the user with shutter glasses does have a fully immersive three-dimensional experience. Although this brief overview of system capability has permitted an understanding of existing three-dimensional capabilities for geometric synthesis, the Naval Research Laboratory would be happy to host appropriate professional demonstrations in which the user can synthesize designs in a fully immersive three-dimensional environment. By developing geometry for a mechanical design in an immersive three-dimensional environment, the engineer or naval architect can experience and review their design in new ways. This spatial feedback allows more rapid and effective generation of a higher quality design, and holds the possibility of giving new tools to those who design and construct Navy ships, aircraft, and other complex mechanical systems.